Okay, here's the plan for the day. So tomorrow I'll give you a chance to work a little bit. You can wrap up the test if you need to. You can work on the new assignment you're going to get today if you want to. What we're going to talk about today, this is not much of a stretch. This is really just a slight nudge above what we were talking about for a long time in chapter 6. So we're going to look at statics and dynamics, right? We're going to look at resolving forces, but this time we're going to throw a new wrinkle. This time it's not going to be so convenient. All the forces are not necessarily going to be acting perpendicular to each other. So let's look at, this is kind of an interesting, there's some good physics going on here that is really relevant right now, this time of year, with all the inclement weather that we're having. So we'll relate this back to something that you're likely to see like next Sunday night when we're done with this. Don't let me forget about that. So here's the situation. We're going to take we've got this 168 Newton sine. So what kind of a quantity is that?
Force.
That's a force. So that we must be referring to what then?
Gravity.
What do we call that? Weight. Weight. That's the weight of the sine, right? Force of gravity. 168 Newton sine is supported in a motionless position. So it's at rest, right? So what do you think the net force is going to be acting on the sine here? Zero. Okay, good. By two ropes that each make a 22.5 degree angle with the horizontal. Okay, you with me? Okay, so it's going to be something like here's the sine hanging here, right? Like so, and then there's some ropes that are connected like so to support it. Okay, so here's a picture, right? We want to know what is the tension in the ropes. Well, anyone want to make a guess?
Like 47.
47. It weighs 168 newtons.
47.
47?
Is it
84?
So 84 is a good guess. Seems reasonable, right? Each one supports half of it. Let's see what happens.
What about the gravity?
It's going to be.
Does everybody agree that's our picture?
Yeah.
Okay.
I wasn't actually late though. I walked in the door.
I'll tell you what I'll do, if it's helpful, I can make a PDF of all the pages on the notes here, and I can put it online for this, for this, would that be good? Because there's a lot of pictures on this one, so, yeah. I am recording it, yeah. Okay, so, attention up here, please. So then, this is what it looks like, right? So our goal then is we've got to take this situation and draw a free body diagram, first of all, right? Okay, so would everybody agree that's maybe a good first approximation of our free body diagram right there? Okay. What do we got here? Well, we've got tension. I guess I should call it F sub T. We've got the tension in both lines is the same. Okay. They're pulling at angles of 22.5 degrees with respect to the horizontal. Does that make sense when we say with respect to the horizontal, we mean with respect to a horizontal line, right? And then we've got this 168 Newton weight pushing down. It's not necessarily drawn to scale here, right? Okay, so what are we going to do about this, though? This looks similar to the stuff we dealt with before, but what's really maybe problematic about this?
It's at an angle.
It's at an angle. It's at an angle, right? Exactly. So now let's talk about for a second why it is that it was so nice that the forces previously were not, or were always perpendicular to each other. Right, if we were to go back, I'm just gonna, right, so if we took an example of, let's just say we had something like, for example, a crate that's being pulled with a tension, some tension in that direction, and the weight is acting down, and the normal force is acting up, and then there's some frictional force acting behind it, something like that, right? We did a lot of that kind of thing. Okay, does the weight have any impact on the horizontal net force? No. Does the weight? Not directly, does it, right? Because the weight is pushing perpendicular to the horizontal, right? The only way that a vector can have any impact on another vector or on a given direction, motion in a given direction, is if there's some component of that vector along the direction, right? So in this case, think of the components as being shadows, right? So if I were to, for example, if I were to shine a flashlight straight down on this, wouldn't you agree that this tension vector is going to cast a shadow on the x-axis? So it's definitely got some pretty significant component that's acting horizontally, but if I shine a flashlight horizontally, it would cast a shadow on the y-axis, right? So it's actually got components that are acting in both. So it sort of contaminates, not as it contaminates, but it plays a role in calculating both the horizontal and the vertical net forces. See, we had the luxury before of not having to worry about that, because if I shine a flashlight straight up on the x-axis here, does that cast a shadow? No, not at all, right? There is no horizontal component to that one. And it's the same for all those, isn't it? Right? All the vectors acting there. So we've got to take this guy then, and we've got to break this probably into components, don't we? This ought to look somewhat similar. It's been a while since we did this, but remember we did a section earlier in the year where you did a lot of vector resolution stuff, right? Where we had a bunch of different vectors acting, and you had to break them into components and make the table, and then add the components up. This isn't that complicated. It's not like we have so many vectors acting here, but it's the same idea, okay? So suggestions, what might we do with this vector right here? Say it again?
Turn it into a triangle.
Okay, make it into a triangle. We're gonna break it into components, right? So we could break it into, and before we do anything, we want to identify, okay, what are our orthogonal, that's kind of a 10-cent word there. Means perpendicular. What mutually orthogonal directions are we going to use probably in this picture? So we've always used, in the past, in every situation we've had, like the x direction and the y direction being the two directions that we used when we broke up our forces into net forces, right? So what do you think, is that going to work here? Yeah, it would, wouldn't it? That makes sense, doesn't it? It makes sense to break this into horizontal and vertical components, doesn't it? How come? Before we go any further, let's just talk about that for a second.
There's no third.
Okay, there is no third dimension, so we only need two, right? We only need two orthogonal directions that have to be perpendicular to each other. But horizontal and vertical makes sense because one of these forces is vertical, right? Does that make sense? The other two aren't, but that's okay. We can break them into components, right? It just seems logical here that because gravity's pushing down and this thing isn't going anyplace, that x and y directions are the logical choice for our two different perpendicular directions that we're going to break this up into components for. That was kind of an awkward sentence, but you get the idea, right? So let's take this guy. We're going to break him into a horizontal component, which we could call, if we wanted to, maybe t sub x, right? And a vertical component, which we might call t sub y, and those are going to be at right angles, right? They're perpendicular. I could do the same thing over here, couldn't I? And it's kind of nice that really the work's going to be the same for both of those, isn't it? So we'll take this guy over here, do the same thing. So there's another t sub x, and there's another t sub y. Okay, good. All right, that's much better. So effectively what we've done is we've traded those two oddball vectors that were at weird angles for their components, which are at right angles. Now, if I just rewrite that free body diagram, I could make it look a lot better then, couldn't I? Because I'm going to make a trade. I'm going to trade this guy for those two, and this guy for those two, right? So what's that going to look like then? Let's redraw this. And this is what we're going to call this is our initial free body diagram. Sometimes you call it the true free body diagram, but this is the one we want. This is called, if you want to really sound smart here, so you want to drop that one to impress your friends. You're going to make it, when you're doing your work, what do you do? Oh, I'm just making an orthogonalized free body diagram. That sounds really good. So what do you think that means then? Orthogonalized.
You broke it down into components.
Yeah, all the components are gonna be at right angles, so it'll be just like the problems we dealt with before, right? So here's our object. What have we got? Well, we've got, what's that? What am I gonna call that one? What do we call it, T sub x, right? And then we had one there that was a T sub y. We had another T sub x over there, and we had another T sub y. Let's add those tip to tail. And then we had, that guy was 168. Let's just write down, because it's given to us as a number, we'll just write that down as 168 newtons, right? So that's much better. All we gotta do is probably, instead of calling that T sub x and T sub y, we gotta go back and break those into, we gotta use trig, right? To write those in terms of the angle and maybe t, right? So what is T sub y gonna be? If this is a right triangle, what's T sub y gonna be in terms of the angle 22.5 degrees? You remember how we do that? No, let's do any of that, not quite that fancy. Right, when we calculate the components, and let's just go back for a second here. If we want to calculate the components, let's refresh our memories on this a little bit, of some vector, let's just call this vector v, and let's say that's a 40-degree angle, right? So we could call this v sub x, and this v sub y, and SOHCAHTOA tell us. Remember, the components are going to be, how are they going to, the magnitude of the components is always what compared to the magnitude of the vector?
What would it be?
The components, each one of them is smaller, right? Or maybe equal to if there's only one component, but it could never be bigger, right? Components are always smaller than the vector. So multiplying by sine and cosine makes something smaller, right? Because sine and cosine, those functions have output values that are always going to be less than or equal to 1, right? And if you have that trig, I mean, that's no, but we talked about this earlier, right? So we know we're always going to multiply this number by either sine or cosine to make it smaller for each of the components. We just have to figure out which one goes with which. Well, what does SOHCAHTOA tell us that this one would go with? Yeah, cosine. Cosine is adjacent over hypotenuse, right? So this one would just be v cosine theta, and theta is 40 in this case, right? And v sub y, that's opposite of the angle, right? So this one would be whatever that magnitude is times sine 40, right? Okay, so what about our situation here then? T sub y, the angle is right over here, isn't it? Right, that's the angle we're talking about. So there and there. So what's that going to be? What's the magnitude of the vector? Not v this time though. T. Sine, because it's opposite, right, of 22.5. Right? Is that ringing a bell? Okay. And then T sub x would just equal T.
What if we not leave T sub x?
You don't really need it, do you? Because they're just going to cancel, aren't they? If we did calculate it, that's what it would be. But look what our horizontal equation of motion is going to be. T sub x minus T sub x equals 0. Well, duh, right? I mean, it's, of course that equals 0, right? So we don't need to know it anyway, okay? Over here we got the same thing for T sub y though, right? So then, when we write our equations of motion down, yeah, it's kind of, we have sort of a wasted equation of motion. We know that the net the x component of the net force doesn't help us. That equals 0. Okay, big deal. But what about the y component? That does help us.
2ty.
Okay, good. I've got ty plus ty acting upward. Same thing as 2 times ty, right? So we get 2 t sub y minus 168 equals 0. How come 0? It's not moving. Good. Okay. And we said t sub y was just t sine 22.5, right? So then look what we get. We make that substitution, we get 2 times t sine 22.5. If I add the 168 to this side, equals 168, right? Now what? Divide by 2, good. Tell you what I'm gonna do, I'm running out of space. So I'm gonna do this. Okay, so if we divide both sides by 2, we just get t sine 22.5 equals, whoops, 84. Last step.
84 divided by sine.
Yeah, okay, good. Now, sine 22.5 is just a number, right? That's a calculator number. So we're just going to divide both sides of this equation by sine 22.5. And so those cancel, and I get t by itself, and that's the answer, right? And what should the units be? If it's a tension? Newtons, that's a force, right? Okay, so let's see what we get.
219.5.
About 219.5.
Sorry, we can only use 3.
And yeah, how many sig
20.
figs did we have? I think there were 3, right? Or was it 2?
I don't know.
3.
Yeah, so 220.
So roughly 220 newtons. Well, what happened? That's a lot. I mean, look at this original equation. We're just trying to hold up a 168 Newton sine.
The space ghosts.
How can each one of these tensions have to be so big?
Well, because they have their own mass too.
Such a steep angle.
Okay, we could even assume that the lines are idealized so they're massless, but there's something going on there.
It's
Because they're at an angle, yeah. Because look, of that entire tension, how much of that tension is doing the useful work of lifting up the sine? Only a small fraction of the total tension, right? So a lot of that tension is wasted because the lines are just pulling against each other, right? So why do you think it is then, I remember to talk about this, we're supposed to be getting possibly an ice storm on Sunday night. So if we get an ice storm on Sunday night, it's likely that you could lose power because the power lines might snap. How come?
Because they're at an angle.
Because they get covered in ice, and it's sort of like this, isn't it? You get this power line with a bunch of ice near the middle of the power line, and that requires a tremendous amount of tension to lift that heavy ice, and at some point, either the power poles aren't capable of supporting that if they're a little bit flawed, or the wires just snap. If there's if there's some kind of a defect, which there are tons of them, in the lines, then they just snap and you lose power, right? Okay, there's another thing that could help you out here though too. Let's think about this, just this simple concept. Does that make sense? Okay, so if you wanted to prevent, if you were an engineer working in, we're supposed to be building this great new power grid. We need to. We've got the worst power grid of all industrialized countries. So we're supposed to build this new electrical grid system. Let's say you're an engineer working on that, making big bucks. If you're building power lines in Montana, where there's going to be a lot of ice, what are you probably going to have to take into account when you design how
The distance between the poles.
distance between the poles, and also maybe how much sag there is in the lines, because you don't want them, you don't want it to be too straight, do you? You want this angle to be a little bit bigger, right? The bigger the angle is, look at our work that we did algebraically. If I put something like the sine of 60 degrees down there, that'd be a little ridiculous, but if I put the sine of 60 degrees, that's just 1/2, right? No, it's square root of 3 over 2, right? Even if I made that 30 degrees, it's gonna make it a little better. If I made it move from 22.5 to 30, sine of 30 is 1/2, and so that would make this 168 instead of 220. Even that little bit of a change. See what I'm saying? Okay. So yeah, you're gonna wanna probably do a lot of calculus and figure out, okay, so what's gonna be the most cost effective here? We can afford to have a few ruptured lines, but we also don't want it, the bigger that angle, the more cable it's gonna take to stretch over all these distances, and so we got the cost of the cable, and now you got a big math
It's
problem.
almost like we want an influx.
Inflection point?
Inflection?
There you go, there we go. Right, what about this one? Let's say here's another possibility, so you're driving up to go skiing at Anthony Lakes, and roads are bad, you get stuck in the deep snow somewhere, you swerve off the road and get stuck in the deep snow. All you've got available to get you out of there is, maybe you got a tow rope in your car, and
Snowboard.
that's about it.
Snowboard?
I've been in that situation.
Have you?
Yeah.
Okay, how could you use like a tow rope, let's say? How could you, if you just have to get your car nudged a little bit to get it onto where it'll have a little traction? How could you use a tow rope, and let's say you're up by a bunch of trees and things, you know?
You wrap it around the two trees so it crosses over the road so that any cars coming by get stopped.
No,
You can ask
no.
for help.
But what about this? What about this one?
Wait for a car to come by and run back.
So here's the tree. There's the tree, and here's your car.
Yeah.
Yeah, a little tiny car.
You ever come
What could you do?
along?
Okay, maybe. But even if you did, you could make this a lot easier. You could take your tow rope and wrap it around the tree, like so, right? Make it tight,
Sit on it.
as tight as you can, and then what direction would you pull?
That way.
Pulling this way is not gonna be very effective because you're gonna have to apply an awful lot of force. But what if I pull in that direction?
Oh.
Right, what's that gonna do? Right, so there's practical applications of physics here. What's that gonna do? If I pull in, look what happens. If I pull in this direction, look what happens. I get these really large tensions in the line, right? Because that angle's pretty small. So you can generate really big pulling forces,
Is that what you did?
right? And so what you'd probably wanna do, if you had somebody else up there with you,
Now
And
that
this
he
is-
explains it.
I did this once. This really does work. I got stuck in the snow and that's how I got out.
Wait a second. You're teaching us.
You grab a rope and pull.
So what you do,
Tell his story, Ian.
so what you do is you pull on the tow rope, and the car budges a little bit, someone puts a wedge under the tire. You tighten up the rope again, so you get the angle small,
You just
pull
keep
again,
going
and
slowly,
you just ratchet
surely.
it that way, and you can pull a car out that way, seriously, without much force.
Wow. And people ask what's the application of school.
Yeah.
There you
You
go.
just gotta get to the higher levels.
All right, so,
All right, class is done. Get out of here. You can go home.
okay, how about this one? Start another one.
Stuck on the side.
So a truck weighing 500, or trunk, not truck, it's a light truck. Trunk weighing 562 newtons is resting on a plane inclined 30 degrees above the horizontal. It's resting, right? What's the net force? Zero, okay. All we want to do here, let's just practice drawing this picture. Find the components of the weight force, mg, parallel and perpendicular to the plane. Okay? So,
We're talking about like we're talking about like an airplane or like a
No,
plane.
a plane inclined like
inclined plane.
So just on a slant.
Oh,
Yeah,
that's what I
okay.
was thinking.
So there's our picture, right? Okay, I want you to notice something about this picture here. Okay, there's the trunk resting on the inclined plane, right? Now, in this case, if we were to, let's graph, or let's add all of the force vectors that would be applied to the trunk. I can't remember, did I have, oh yeah, I thought I did. Nice. I knew I did something tricky here. Okay, so that's the 562 newtons, correct? Pushing down, that's the weight of the trunk. What are the other forces acting on the trunk?
Friction.
Okay, there is some friction. In what direction is the frictional force going to be acting? It's going to be acting up the ramp because it's preventing it from sliding, right?
Right.
So we've got a frictional force acting in this direction. And what kind of friction is it going to be? Static, it's at rest. Okay, and what else? Got gravity,
Natural.
that's the weight.
But you have, wait,
Sliding.
Isn't there one?
Normal force, right?
Wow.
There has to be, you throw your voice up there. There has to be a normal force or the crate would just fall through the plane. But that doesn't really happen. It is a ramp, right? It's a solid ramp. So the ramp must be supporting the crate. In what direction is the normal force acting? Perpendicular to the surface. Normal means perpendicular. So the normal force is acting like that.
Is that what makes it slide down? Or is that the?
No, the normal force is what prevents the object from falling through the surface. Right?
Gravity.
It's the support force.
Okay.
Gravity is what's going to make this thing slide this time, isn't it?
Okay.
If it slides. Yeah.
It would slide because gravity's pulling down and the normal force is pushing this way, so it'll slide.
Well, the
down
normal
towards
force-
the normal
Okay, the normal force is pushing perpendicular to the plane, right?
Yeah.
So it's going to have no impact on the horizontal motion, right? The frictional force will resist the horizontal motion, but there is going to be a component of the gravity that's going to be pushing this thing down the ramp, right? If we break it into components. Now, the next question, though, is what's going to be our logical choice of our orthogonal directions here? The X and Y really fit this time. They don't fit, right? They really don't fit very well this time, right? We want to do maybe what? I mean, if you look at these forces, 2 out of the 3 forces are lined up either parallel or perpendicular to the plane, right? So why don't we adopt those as our
Just do a
directions?
sign and then just do that, and then as long as it's bigger than that, you're good. You're good.
Say it again.
So do the sine thing so you can get the hypotenuse, which is the force that's gonna be pulling that way, and then figure out the static force and whether or not. it'll be
Well,
able to
yeah,
do
we're just,
that.
all we gotta do is break this into, we gotta break this vector into perpendicular and parallel components. Notice the subscripts up here. Usually that would have been an X and a Y. Here's how I like to do this. The book doesn't do this, but this is the way that I did it all through college, and I feel like this is a good way to kind of remind yourself what's going on. That's just a symbol for parallelism, right? So that's just saying this is the parallel direction, and that's the perpendicular symbol, right? So those are gonna be our orthogonal directions. So instead of saying like F sub X now, we're gonna talk about like F sub parallel, or F sub perpendicular, right? Okay? So then all we've gotta do is just take this vector, right, and we're gonna break this into perpendicular and parallel components that add tip to tail to give us the original vector, right? So it's gonna look like maybe something like that and like that, and that's a right angle. So we would call this one, well, it's 562. So we'll go ahead and just, okay, one other thing we gotta do. We gotta figure out where that angle shows up. Kind of jumping ahead just a little bit. Now, when we draw this picture, this angle down here, let's just call it theta, it's 30 degrees. Yeah, the other one's 60, isn't it? So we gotta figure out then, doesn't it make sense that one of those angles must be 30 and one must be 60? Let's take just a second and talk geometry and remind ourselves how we know that and which one's which. So what do we got going here? We've got a right triangle and a right triangle, right? Agreed? They share one side, and they're both right triangles. And so, what does that mean?
That means they have
There's a bunch of things going on here. So we know, let's look at this. We know this is a right angle, right? Everybody agree? And that's a right angle, and that's a right angle, right? So if this one's 30, what's that little angle up there? 60. Okay, but if that's 60 and that's a right angle, that means they're complementary. So what's that angle in there? 30, right? Which makes this one 60, right? Right? Okay, so here's how I think here's a good working way to remember how this works. You know that whenever you have a situation like this where you've got an inclined plane and you're breaking up the gravitational force into components, you know you're creating similar triangles. It's not always the easiest thing to remember that the 30 degree angle goes with that angle up there, right? That's tough to do. What you can always do though is apply the principle of exaggeration. This is the best trick in physics. So even if, like, what if this angle were 44.5 degrees? Well, then you can't tell which angle's which, right? Redraw the problem maybe like this. where there's one clearly very acute angle and one that's a lot bigger, right? And then you can see small angle goes with small angle, big angle goes with big angle, right? See how that works? So that way you can, if you just exaggerate the angles, you can see which one goes with which pretty easily. Does that make sense what I'm saying? Okay. So then that's my 30-degree angle, right? And so if that's a 30-degree angle, let's write these components then. What's this component right here going to be? The perpendicular component. 562 times, there's my angle, sine or cosine? Cosine, because we're dealing with the adjacent leg, right? So 562 cosine 30 degrees. And this guy down here is going to be 562 sine 30 degrees, right? Does that make sense? And so if we wanted to create an orthogonalized free body diagram, that wouldn't be a big deal. Let's just do it right here. So we'd end up with, there's our object. We've got our frictional force acting in that direction, right? We've got we've got a component of gravity acting in that direction. That's going to be the parallel component, so that's 562 sine, I'm just going to call it theta, so I don't have to write too much. And then we've got a component, a perpendicular component of gravity that's 562 cosine theta, and we've got our, we've got our normal force acting like so, right? Okay, so I want you to tell me something about this. Does that make sense? Do you think the normal force is going to be greater or less than, in this case, it would be if that inclined plane were actually flat? What do you think?
No, I didn't think I was.
Okay. So try to answer this one first, and then I'll get to yours. So I want to know, is the normal force here bigger than or less than it would be if we tip this down so it's flat?
That's because
It's less.
So you have to,
Yeah. How come?
I think, I don't know, gravity.
Okay, because these two are being shared, these are shared components of gravity, right? If I tilted this thing down, would you agree this one's gonna get gradually smaller and that one's gonna get gradually bigger? Until eventually that one disappears and this becomes the entire weight? Does that make sense? Right? Only a component of gravity is being offset by the normal force here. And think about this, if you were pinned underneath a crate, and you would rather that the ramp you were lying on would be a little steeper, right? So there'd be less force pinning you down to the crate. Does that make sense?
That's like when you try and move like a washer, for example, you can't hardly move it when it's on like flat, then when you tip it up, it's a lot easier to handle.
Or if
Because
you're rolling it down a ramp to a moving van or
Yeah.
something, or,
Or if you
right?
just throw it down.
Okay, yes, question.
So how come when you did like the 562 sine and then 562 cosine,
Mhm.
like how did you know to put them?
Okay, because let's take this triangle and just make it bigger. So that triangle looks like this. This is a 30-degree angle, and that's a right angle, and this is 562, right? So this is, if this is my angle, this is the adjacent side and that's the opposite side. And so by SOHCAHTOA, we know that sine goes with opposite, cosine goes with adjacent,
Yeah.
right? And so that's why this one would be the cosine.
Well,
It'd
yeah,
be,
but like on the, when you drew the,
that, right there.
No, like back to the first one, the one you drew just now.
Tell me when to stop.
Like when, yep, keep going,
Page here.
keep going, keep going. Yeah.
Okay.
When you do the free body diagram,
Mhm.
like the top one, how do you know to put the,
That one there?
yeah, like
Okay.
where to place those?
Okay, because, here's why. Because look, that's this vector, isn't it? Right? See what I'm saying? That vector is that vector. What do we do to this guy though? In a free body diagram, the vector is all tip to tail. Yeah, we just scooted it up to
Oh,
there.
no, this is the wings and it's parallel.
Right. Right, the parallel one got slid up to there, so it starts at the object. 'Cause all the vectors have to start at the object or get added tip to tail with another vector that started there, right? Okay, good question. Okay, All right, how we doing for time?
Got 7 minutes.
7 minutes, okay, got one more to look at. This guy. So a 62 kilogram person, you like all this skiing themes and so, you like that? I like to be thematic in my teaching. So a 62 kilogram person on skis going down a hill, sloped at 37 degrees. The coefficient of kinetic friction between the skis and the snow is 0.15.
We should calculate crashes.
Crashes? We'll get to that.
That'd be sick.
How fast is the skier going 5 seconds after starting from rest? Okay? So if the skier is going down this hill, what are the forces acting on the skier? Gravity? Normal force? Friction. That's it, right? Okay, so would everybody agree that's what the free body diagram looks like before we orthogonalized, right? Here's our hill. This is the parallel direction, that's the perpendicular direction. Normal force acts perpendicular, frictional force acts anti-parallel, right? Opposite direction. And the gravity, though, needs to be broken into components, right? So we take this gravity vector and we break it up into the perpendicular component. And if this is my theta up there, is it going to be multiplied by sine or cosine? Cosine. So this is going to be FG cosine theta, and this is going to be F sub G sine theta, right? So when I build my orthogonalized free body diagram, it just looks like this. We've got normal force opposite of force of gravity. They tell us what it is. 62, so mg, right? They give us the mass. The weight is mg. So we would just call this mg cosine of 37, right? Okay, we've got this guy is going to get slid up to there, right? So we've got a vector pushing in that direction that's going to be mg sine 37, and then we've got a frictional force pushing backwards, a kinetic frictional force, right? Make sense? Everybody buy that? All we did was just took this one and slid it up to there. Otherwise, it's the same, right? We traded this one out, so it's gone, and moved that guy up there.
Is the 37 part of the question?
Yeah. 37 degrees. Okay? Coefficient's 0.15. So now let's use our equations of motion. Let's build our equations of motion. What's going to be the perpendicular equation of motion? So there's the positive one, right? Minus that equals, or plus, yeah, minus that equals 0, because it's not accelerating perpendicular to this.
Would it
slope.
be mg sine 37 minus cosine or the friction?
It's going to be these two. These are the two, because this is, remember, this is, and here's kind of a way to remind ourselves. That's the perpendicular direction, and that's the parallel direction, right?
Yeah.
Okay, so then we could say that normal force minus mg cosine 37 equals 0, and all this really is just the perpendicular component of the net force, right? So there's one equation of motion. What's that tell us if I solve for normal force?
Normal force equals that.
Equals that, right? So this is really telling us normal force equals mg cosine 37 degrees. Let's look at the other equation of motion. Let's look at the parallel equation of motion. We said that was the positive parallel direction we defined as being down the hill. So which one's going to be positive then?
It's going to be the mg sine 37.
Yeah, okay, that's the positive one.
That's going to be that minus the FK equals the net force.
Minus kinetic frictional force. Well, what is kinetic? We'll kind of speed things up. What's our formula for kinetic frictional force?
UK
U sub
K
Times normal force.
Yeah.
But what's normal force? It's regular.
Sine 37.
and then that equals F of net, which is mass times acceleration.
Good. So really what we needed to do here, we're not going to finish this, but let's at least talk about how we could. We want to know how fast is the skier going after 5 seconds. This is a kinematics problem where we need acceleration, right? So we're using our new physics, right, just to solve for A. All I've gotta do is divide both sides through by M, and look, it cancels, right? It cancels, right? And so I just get G sine 37 minus mu G cosine 37 is what A is, right?
And then is A our answer?
No, A is what you need to get the answer, right?
And
Then you gotta do kinematics.
Which one do we sub A?
Oh, who knows?
Who cares?
What's it gonna be? We got, well, we can figure out. We got T, we've got initial velocity 0, and we know A, so it would be, and we're looking for final velocity, so it would just be that guy right there, wouldn't it? M2, right? It's a lot of stuff.
Wow.
Okay.
So it'd just be A times